So here's an interesting example of a random process. In 1777, a French man named Comte de Buffon talked about dropping a needle on a piece of paper. So the needle has length 1, and the paper has ruled lines, so just horizontal lines, that are length 1 apart. And Buffon asked, if you drop the needle on the paper, what is the probability that the needle is going to intersect one of the lines? This experiment they did experimental trials, and they also calculated this mathematically. And it turns out you can actually use this, possibly, it's not very efficient, but you could use this to estimate pi. All right, so there's two ways to figure out this needle problem. First is to actually perform the experiment, meaning you're just going to take a needle, you're going to drop it on the paper, and you're going to keep track of whether the needle intersects the line or not. You do this many, many, many times, and you have a good sense of what the probability is. You just take the successful trials over the total trials. We call this a Monte Carlo process. A little bit cumbersome to do in real life. It takes, about a second to drop the needle, another second to pick it up, maybe a second to record. It's kind of slow. We do have computers now, which can simulate physics, and can simulate real life things such as buying things in stores, like what amount of customers will come in and how many of them will buy things. So on the computer, when we run something related to real life, we call that a Monte Carlo simulation. Useful tools in mathematical modeling. In this case, with Buffon's needle, we can also solve this with math. So let's look. We have, pretend this is just 2 of the lines that are 1 unit apart on the paper. So like there would be another line down here, and so on. And then, so that's 1, and we'll call that the needle. Is that about the same length? Maybe. Okay, there's the needle, and then here's the midpoint. So there's 2 random variables involved here. And to just take a minute to convince yourself that these are independent variables. One variable is the distance from the midpoint to the closest line, which we'll call big D. And that just tells you basically where the needle fell. And then the other variable is this angle theta, which is the angle the needle makes with the horizontal. And either of these can change in any way. Okay, and so then let's look at this vertical distance is going to be, so if the needle has length 1, then this half the needle is length 1/2. There's that hypotenuse, so we can use this right angle triangle to solve for this height, which was 1/2 sine theta. So it looks like the condition for crossing the line, crossing the closer line, d is the distance to the closer line, is d is less than or equal to 1/2 sine theta. Right now we see that d is more, so the needle doesn't cross. If d were less, the line would be closer, the needle would cross. And then we note a couple things. D is between 0 and 1/2. Distance to the closer line has to be at most 1/2. And theta is, we could have said between 0 and pi over 2. We could say between 0 and pi. Once I draw the picture, you'll see that it doesn't matter. So between 0 and pi, meaning we're always going to take the angle with basically like the positive x-axis. So if the needle's, I'll draw it over here. If the needle's over here, then that angle's theta. There's the horizontal. Okay. And we'll assume that these are uniformly distributed, meaning every number between 0 and 1/2 is equally likely. Every number between 0 and pi is equally likely. Because you're just dropping the needle randomly. Okay, so then we can graph this. We'll call this the d-axis and the theta axis. D goes from 0 to 1/2. Theta goes from 0 to pi. And then we want to graph this inequality, basically. So here's d equals 1/2 sine theta. Here's about pi over 2. I did not make use of this graph paper at all. Sine curve looks kind of like this. It intersects. If we kept going, it would go down and back up. Okay, there's 1/2 sine theta. And d is allowed to be anywhere from 0 to 1/2, theta anywhere from 0 to pi. So we're in this rectangle, which that curve is tangent to at one point, horizontally. Less than or equal to 1/2 sine theta is down here. So this is a geometric probability, meaning here's our successful region, here's our total region, and so the probability is just going to be the area of the shaded region over that whole rectangle. Okay, well, we can calculate this with some basic calculus. We're going to integrate from 0 to pi 1/2 sine theta d theta. That should be negative 1/2 cosine theta. Theta goes from 0 to pi, so negative 1/2 times cosine of pi is negative 1 minus cosine of 0 is 1, which is a total of negative 1/2 times negative 2 is positive 1. Okay, area of the shaded region is 1. Area of the rectangle is 1/2, that's my dog sneezing, 1/2 times pi is pi over 2. So our probability is going to be 1 over pi over 2, which is 2 over pi. So a little bit less than 2/3 of a chance of the needle intersecting the line. Kind of cool. If you ever are not near any computer or anything that can give you a few digits of pi that you need, all you need to do is take a unit length needle, a ruled piece of paper with lines that are 1 apart, and you throw the needle onto the paper many, many, many times, and calculate the probability. Take 2 divided by the probability. You will get an estimate of pi.